Okay, yes, so we are now live. Good afternoon, everybody. Thank you for showing up physically and also for those online. This afternoon, we've got 3 lectures, okay? The first one is looking at where composites are today, particularly with regards to sustainability and those kinds of technologies, okay? The second lecture will be on sustainability strategies and the circular economy, and doesn't really mention composites at all. It's a very general lecture, okay? Then the third lecture will be towards sustainable composites, looking at recycling, bio-based materials, some emerging end-use sectors, hydrogen tanks, for example. So some of these guys can come and give the lecture because they now know more than I do. We'll look at a bit at 3D printing. So the first lecture will be around 40 minutes, take a 10-minute break, and then we'll do the next one, 10-minute break, and then do the next one. And particularly in the second lecture, I'll ask you questions. Just put your hand up if you've heard of things. If you haven't, it helps me to know what you already know. And again, you may know more about some of the topics than I do because we're all learning together, okay? So to the first lecture around composite applications, see if all the technology is working today. It's got a bit complicated because that's really a bit of a problem if the this doesn't work. Demonstration effects. See if the mouse will work because I have lots of animations. Nothing works at all. Very strange. Okay, this is going to be rather painful if I can't use the pointer. So here we go, it works now. So you can look at composites used today in what I like to see as 2 main categories: mass adoption of composites and mass production. Mass adoption means there's lots of tons of it being used. It doesn't necessarily mean there are hundreds of thousands of parts being made. So if you look at aerospace, it's mass adoption. Not very many airplanes per type are made, but there's a large amount of composite being used. You can look at wind turbine blades. They're very large structures, but we're not talking about 200,000 Mercedes C-Class per year. We're talking about relatively lower numbers of blades. Second way we can look at composites being used today is in mass production. Supercars, not really, that's more mass adoption, but starting to look at where BMW have gone with their i3. We start to see composites in consumer electronics. We see composites being used in compressed natural gas and in the future hydrogen type tanks, and also in automotive in higher volumes. So 2 ways of looking. And as we go on to look at the circular economy and sustainability strategies, we need to think about how we can apply those to these kind of 2 classes of material. And I want to give you a little bit of industry landscaping. This is a macro chart, which looks at basically dollars by different material types across the top and different industrial sectors. And what I want you to look for is the big ones, okay? That's where we can make the biggest impact as we go forward looking at composites. So in terms of dollar value, commercial aerospace is very big. Wind is here with epoxy and a bit of carbon and some glass. Commercial aerospace, yeah, you've got your sporting things in here as well. They are there, they are important, but they're dominated by mainly aerospace in this picture, okay? So that's where composites are mainly used today on a dollar basis. So it's important that we look at the aerospace industry. Another way of looking is looking at some more of the constituent material types. Here you can see a big dominance of resin. That's mainly because it's very hard to separate where epoxy is sold for coatings versus composites. You can see all the injection molding materials that go into automotive, sheet molding compounds, carbon prepreg. So it gives you a picture and some quite hard to find data about growth rates and some gross profits, and you can do some consulting with those slides after the course quite easily. So that's where composites are used, which is why I've chosen aerospace, automotive and wind for a quick look. So starting with aerospace, this is the Airbus A350 fuselage section made in carbon fiber. And what I want to do is to show you a video in just a second from Airbus, because they describe how they see composites in their company, and it's makes it a bit more real for you. This is supposed to be a kind of industrial lecture looking at the more applied side of things, okay? So we use composites in aerospace, yes, to make it lighter, which reduces life cycle costs. It's grown from military into civilization. Now it's in primary structure. It's important because aviation today contributes only 4% towards global warming, but in the future, it could consume a sixth of the remaining temperature budget to limit global warming to the Paris Treaty target of 1.5, because it's going to grow considerably still. What we've seen is increased automation in aerospace, and you'll see this in the video. And composites can reduce the number of parts counts in an aircraft, so you can make the aircraft with less pieces in composite than in aluminium. It also increases the service life of the aircraft, less maintenance. And that's also important in the circular economy, is to make parts last longer. So carbon composites have excellent fatigue and better corrosion resistance, and you can see from 6 to 12 years. So there's real reasons behind why they use composites, not only just to make it lightweighter, it's a more robust structure. So I'm now going to play you the video, and you can just sit back for 4 minutes and listen to this lady talk around. Don't know if they can see this on Zoom or not.
Carbon fiber production was launched at this Airbus factory in Gas, just outside Madrid, 25 years ago. It was the start of a groundbreaking investment in composite material in civil aviation, but industrial innovation in carbon fiber use bears little resemblance to early days. Airbus has made a multi-million-dollar investment in new technology.
It's on my screen, but it isn't showing on the beamer. We have to skip the presentation out and jump. Okay, we're going to have to do that every time.
Carbon fiber production was launched at this Airbus factory in Gas, just outside Madrid, 25 years ago. It was the start of a groundbreaking investment in composite material in civil aviation, but industrial innovation in carbon fiber use bears little resemblance to the early days. Airbus has made a multi-million-dollar investment in new technology, turning this facility into a world leader in composite industrial manufacturing. 700 highly skilled staff work here. Teresa Busto is the plant director.
In my opinion, this is one of the world's more important centers of excellence in composite that we have. We have the best experts in the world. We have more or less 30 patents produced just in the 350 program, Airbus patents, and we consider that we are at the top level of the composite manufacturing.
When the balls of frozen carbon fiber like this arrive at the Gas plant, there are just 200 hours before the raw material perishes. It has to be treated very rapidly. First, the machine build up 0.2 millimeter threaded layers of the composite material with the most advanced machinery that exists anywhere in the world to take the exact shape of the aircraft structure. In this case, the carbon fiber will be used to make the rear fuselage section of the A380. After that, it's heated or cured with a resin mix in massive pressurized ovens known as autoclaves. When they emerge, the large sections are turned into light but strong composite parts. In the beginning, on the A320 program, under 10% of all the aircraft structure was made from carbon fiber. It rose to 25% on the A380, and it's now around 53% on the A350 XWB.
25 years ago, we produced parts by hand. But by hand, usually the person is able to lay up 3 kilos per hour, more or less. So the restriction for that was unbelievable. We were not able to produce part more than 20 kilos or 5 meters or 6 meters long. Today, we are some means that are able to lay 30, 33 or 34 kilos per hour. So you can imagine the size of the parts are biggest and we can produce more complex parts.
carbon fiber weighs significantly less than aluminium, which of course means the aircraft can carry more passengers without adding to the weight. On top of that, the maintenance costs come down too.
Basically, the main advantage is the weight saving. Making parts with carbon fiber, we can save, compared with aluminum, up to around 20% of weight. It is also another advantage that there is no corrosion and there is no fatigue. Okay, and this is a main advantage for the customer, for the airliners, because they can minimize the level of effect, the level in the life of the aircraft.
Nowadays, the whole process of turning the carbon fiber into a composite part into little as 10 days and a maximum at 80. But innovation never ends. New research is the way to speed up the process and bring the weight of the composite parts down even further. These water jets, for example, cut parts without the wear and tear risks from traditional machinery.
We consider Airbus is the world leader for different things. First, material development. Second, tooling, innovation in composite parts, processing of
Okay, so that gives you a little look inside an Airbus plant to see the scale of the operation, the investment in the operation, the size of the equipment, what goes on beyond the fracture mechanics lecture, which is fundamental to all this. Okay, this is what's really happening today. And this is the bit of the history where you can see very early use of composites, mainly on the tail areas, up to the A350, which is pretty much the highest use of composites, with around 55% of the structural weight. And here you can see a change in the processes being used from the 70s and 80s, which was wet layup, then shifting to pre-preg, then going from hand layup to automation, starting to look at out of autoclave processes. You saw that huge chamber. Yeah, that machine is very expensive and the cycle times are very slow. So they're trying to get away from this, and it's a major thrust of composites research. Okay, increases in advanced fiber placement, which was that machine you saw placing the UD material. It gets rid of waste, it gets rid of the labor, it's very precise, the fibers are carefully aligned. So you can see the advanced fiber placement and the advanced tape laying percentages going up, and the hand layup processes going down with time. In the future, the big discussion is around the replacement for the Airbus A320, which is an aluminium aircraft, but it's made at high volumes. So this is the number of units of single aisle aircraft compared to the number of units of large aircraft. And the big discussion is how much composite will be used in the replacement of the A320. So the composite companies like Toray et al. Are trying to capture this business, and it would drive up the manufacturing volume of carbon fiber in aerospace. Okay, and that has big questions also for composite engineers to be able to make aircraft more sustainable. We'll see that in the third lecture. So it's really increasing. Here are just a few pictures that just show you where composites are used on the A380. You can see again the tail's very popular, part of the wing structures. It's a whole range of processes. Some RTM, hand layup, some thermoplastic parts on the J nose of the wing, resin infusion, torsion box. You've got this central wing box that goes between the wings. It's an enormous composite structure. Okay, it's the width of the fuselage, gigantic piece of composite, really enormous. The A350, which is even higher percentage use of composites. You can see the whole barrel of the aircraft is made. It's a challenge for composites because you get impact from stones and debris on the runway on the lower part of the aircraft, and it took them a lot of work to get this to actually work. But now it's a very automated and very precise process. Okay, I wanted you to really see what they've got to, which I think is very impressive. Boeing have done the same thing. You know, they're as advanced as Airbus are. The 787, you can see again, the fuselage section, and you can see some of the different companies involved. So it's a global industry. Military is the same. You can see percentage of composites going up. This is the F-35 fighter, and the entire skin is from composites. This is to save weight. It's also for stealth reasons. They didn't actually make the inside of the aircraft from composites because they're actually making it at quite high volumes. But you can just see the trend with time, increasing use of composites. Same thing with helicopters, but even higher percentages because they're obviously hovering and they have less aerodynamic lift. They need to be even lighter. So almost entirely made of carbon fiber. Okay. Just gives you some ideas. In your own leisure, you can look at these videos, which just show you UD tape being placed onto a flat structure. Here it's being placed onto a curvilinear surface, which is more complicated. This is now possible with thermoset composites and thermoplastic composites. It shows you the complexity of the heads that they've developed. The mechanical engineering in here is really quite crazy. You mechanical engineers know what they have to make this robust to work day after day. Is quite an achievement. And again, you see the A380 structure going into this enormous autoclave that costs millions of dollars. And that's why autoclaves are not allowed in America's Cup, because you'd have two teams, Boeing and Airbus, because they're the only ones who could make a boat in such a large autoclave. Okay, so we use resin infusion and other techniques in Alinghi. I talked about out of autoclave. And this is an example. Airbus have a big program called the Wing of Tomorrow. And here they pre-pregged carbon epoxy tapes using a automated fiber placement machine, like on the last slide. And it applies this material over a male mold. And that is then cured out of autoclave under a vacuum bag. And they can get 0.1% void. So very, very low void content to give you the high mechanical properties that you need. So that's kind of process they can use to place the fibers, and that's the kind of part that they're making out of autoclave. They chose pre-preg versus liquid resin because you get very precise fiber contents in a pre-preg. If you're doing resin infusion with a vacuum bag, you can get some variation, but maybe Veronique solved this, but that's how the aerospace guys see this. But going on to look at liquid resin infusion, people are working on this. Out of autoclave cure, you can cure different parts onto each other with this process. You can get higher volumes and you get rid of the autoclave. It's very nice. There is one aircraft which has the wing skins already made by liquid resin infusion, a Russian aircraft. So that is actually already commercial, which is I find very interesting. So you can read a few more articles in your own time about how they're trying to go out of autoclave using liquid resin infusion techniques to make aircraft structures. Something very, very close to my own interests, using thermoplastic composites. Leah sitting at the back, projects on these types of materials for drone structures. Didn't mean to surprise you there, sorry. So this is made of UD carbon PEEK or PAEK tape that's got a much higher interlaminar fracture toughness than carbon epoxy. It's extremely tough, very good for impact type structures. So here they lay down the tapes using a thermoplastic variant of what you saw, and then they stamp form these in a press by compression molding them. And you can make these kind of structures, obviously with water jet cutting of bits out afterwards. So they use that, they're starting to look at this for its toughness. So that's a really quick tour of aerospace, of the kinds of things that they're looking at, getting rid of labor, going to automation, using these UD materials, out of autoclave processes, interest in thermoplastics, okay? We'll look at the recycling issues in the third lecture, and we'll see that's very embryonic. So going from mass adoption to mass production, this is the B&W i3 safety cage, life cage as they call it, made by resin transfer molding. So back in the 1970s, I know the guys at Ford very well, they made a vehicle made of carbon fiber epoxy. Okay, it's been done for a long time, You might not like the aerodynamics, but the weight saving was still there. But the manufacturing techniques weren't ready for high volume production. This is basically a rolling aircraft or a rolling military jet. Carbon fiber is also used in supercars. So here it's not for weight saving, it's for performance, it's for acceleration, it's for stiffness and handling, okay? It's not to save fuel, because this has a 720 horsepower supercharged V8. It uses huge amounts of fuel, okay? So the most interesting area, I think, is going towards high volume use. And we had a visit once from BMW, and the manager there said that to get to the status of the i3, they spent 3 billion euros on composites R&D in BMW. Okay, so that's a big bale of money, and anyone's counting. It included using hydropower to make the carbon fiber in their joint venture with SGL. So they use high-speed resins, they use automation. They ticked all these boxes to produce this structure, and we're going to look at it in a bit more detail in a moment. But if you speak to automotive companies about saving weight, they all have different strategies. Okay, some say aluminium is really great, some say high-strength steel, and basically they're all correct because their aim is to save weight. Okay, so you can have more than one correct solution. You can both be right. So this just shows you some breakdowns of percentage material for conventional lightweighting, moderate lightweighting, and that's what we're seeing today, really. Lots of use of aluminium. It's the primary go-to material to save weight. And I'm saying this in a composites lecture, but it is a reality. Then extreme lightweighting, you can go to higher percentages. And that's been done on the BMW. But if Audi and Ford and Volkswagen and Toyota all decide to make an i3, what's the problem? There's not enough supply base for carbon fiber. They couldn't buy it. It can't be made. There's not enough carbon companies with capacity to supply it. So that has to be solved if you want to see wider use of these materials. So we're going to look a little bit at some of these materials in a bit more detail, but just to make a point, because many people don't understand this. When I worked in DuPont, the senior managers there did not understand that if you assume 1 kiloton of aluminium sheet is equivalent to a kiloton of composites, okay, just roughly speaking. In 2020, there were 2,000 kilotons of aluminium sheet used in the automotive industry, while there were 20 kilotons of composites. And you divide the two numbers together, and you can see the issue. So if you want to scale up the industry to replace aluminium, which is what the composite guys like to dream about, you go to the JEC and they say composites will change the world. Well, there's a major issue on the supply base. Okay. So that's the current worldwide demand of carbon fiber, industrial, wind, consumer, aviation, automotive. Okay, if you have one part on 4 mainstream vehicles or one body on white at 100,000 per year, you've doubled the automotive demand. If you go to 4 parts on 8 vehicles, you've doubled the world demand. So one thing we need going forward into a sustainable economy is people need to put in place infrastructure. Someone's talking. And that's an issue for carbon fiber, to be quite honest with you, so you are aware of this. So that was looking a bit at the supply issues of carbon fiber. Now we're going to look at which composites are used today in automotive. The most widely used is sheet molding compound. It's been used for a long time. It's got a big supply base. It's a cheap material. You can paint it. It can go through e-coat. It's stable dimensionally with temperature. It's a great material, very established. And you can see here, you can have some structural parts. That's a part of a Ford Transit van being torsion tested, so it could take some loads. And like I say, you can paint it. So it's the most mature automotive composite manufacturing process, but it's chopped random fiberglass, okay? It doesn't have the mechanical properties of the carbon tapes we just saw. It doesn't give you the same weight savings, but it's very stable. It's widely known. And people have gone on to use carbon fiber SMC, where they've made some kind of UD material with some random fiber inside, which can be placed into near net shape preforms. And then you can pressure mold these in under a minute's 90 second cycle time. So you can push these out at high volumes. You can make lots and lots of them. So they're good for mass adoption. And this gives you a lot more weight saving than the glass material. And you can use slightly better resins, vinyl esters, epoxies, rather than polyesters. Okay, so very interesting material. And I think we'll see more of it in automotive. So that was thermoset. Now looking at the thermoplastic equivalent, which is a glass mat thermoplastics. So again, a random glass mat that's impregnated with a resin like polypropylene or polyamide 6 on a laminator. It's made into a sheet, and then you heat it up in an infrared oven, and you put it in a big press, and you compression mold the parts. And these are made in around 30 seconds, 40 seconds, it says here 50, for that kind of cycle time, because the cycle time is only limited by heat transfer. You just got to cool down this hot sheet. There's no chemistry going on, really. It's basically heat transfer, okay, crystallization, and final consolidation. It's a very tough material because it's thermoplastic. It's very good in crash. So if someone drives into the back of your Mercedes, it helps absorb lots of energy because of the way it deforms. And it gives you the weight saving. But you have to assemble it after the electrophoresis treatment because of its melt temperature. So when you normally dip a body in white to protect it against corrosion, those temperatures go up to 200 degrees C, and polypropylene is long melted. Okay, so it affects your logistics chain and how you assemble the car. In our lab, and Pierre Etienne worked on this for many years on the enabling science and the early applications, looking at saying, well, can we combine injection molding with composite sheet materials? So we take a woven textile or thermoplastic, and we can injection mold material on top. Or we can take a UD material and place that with a robot, injection mold around the top. And this research started about 20 years ago, and it ran through some different projects in our lab, going from generic parts that we talked about, simple robotic systems, cost modeling, structural analysis, to making some demonstrators. So that's kind of the early stage research project. You know, this is a story you'll see in a minute that I'm going to bring it to commercialization. A second project where we did a more advanced robotics with some consortium of companies that you see here. And we made these generic pieces. We also looked at a seat structure that we talked about in the cost lecture. We did the structural analysis and started to take it further. One of my jobs in DuPont was to help run this project, where we again made thermoplastic composite sheets in glass or carbon or tape that we would heat up and stamp form. It's a very fast process. These are very thin sheets, so 20-30 second cycle time. You can really bang them out, and it's very tough. And then we over-inject. Here it's in red to make it look nice and pretty. And we installed automated equipment. So that was a demonstration facility. Other people were working on taking carbon tapes, so here carbon nylon tapes, and they worked out how to make a net-shaped preform from a thermoplastic tape that could then be heated up and stamped. So that gets rid of all your waste and gives you very nice fiber directions. And there are now 2 companies who have made industrial cells that can convert tapes into preforms, which can then be compression molded. So these are very interesting because there's no labor, very little scrap. It's very fast cycle times. So ways of scaling up composites to high volume manufacturing. Yeah. So you saw in the cost lecture, if you want to make 200,000 per year, you need cycle times of below a minute. And that means you can't be cutting out the tapes by hand. You need automated equipment. And to implement this kind of technology, you need a supply base. So there is now a whole range of suppliers who are supplying the machines for overmolding equipment. There are turnkey cells. You can call up Engel and you can buy an overmolding cell, which is equipped with everything you need to do this. There are different material companies that you can buy laminates and tape from. Companies have developed finite element approaches to simulate these materials and to include the tough failure modes of the thermoplastic resins, because they are different to epoxy materials. Very good in crash. So we see now this has gone all the way through to early OEM developments. This is a glove box, which has what they call an organo sheet. This is a part from Porsche, which is a central tunnel of a vehicle. This is a B-pillar of a vehicle, multi-material system, steel and composite mixed together. This is a door module that has UD tape inside it. So these are early applications that are now coming out of these kinds of materials. And I'm going to dare to try another video because I want to show you this process running.
With the RockLock quick change system from Fitaccess, you can simplify your program.
You have to put up with the adverts because
Reduce your.
You get all kinds of bizarre adverts. How that part is made, just so you with your own eyes. Stop. So that's the combination of structure and function together. So you can see it's gone all the way from early research to commercialization, and you can now make composite parts, very short cycle times for automotive type applications. Going on to look, I'm going to have to speed up a little bit, but body and white structures for vehicles, it's more demanding than glove box housings, and you have to consider these are the kind of questions. One of the key ones is that aluminium and steel are very nice materials because their properties don't change across these temperatures, and composites do, depending on which polymer you use. It has to withstand the eco temperature and the chemicals that the vehicle will see. So nylon 6,6 you can't use on the outside of the vehicle because road salt affects the polymer. So different limitations. And we've had some other projects in the lab looking at a steel vehicle going to a composite vehicle. This was sponsored by the European Union, working with Volkswagen. And you can see here we've gone from 28 parts in a steel floor pan to 1 with carbon epoxy RTM. So you get massive integration potential, a huge reduction in parts counts, big saving in weight. And you get rid of that huge automated assembly line that you need for metal. And that's one of the biggest advantages. So BMW, as I talked about, they've invested in automation for RTM. And they've also looked at high-speed resins. And we've talked a bit in the lectures about the effect of the cure kinetics of the resin on the cycle time. In the cost lecture, 10 years ago, 15 years ago, we were at 10 minutes cure. Now we're down to 90 seconds, less than 2 minutes, 1 minute. Okay, Hexcel prepreg used on the BMW 7 Series is now in curing in under 2 minutes. So it's got really fast, which means you can make more parts per year from one tool. And this is the kind of chemistry that's enabled composites. Here's some, some of them you have to watch the thermal exotherm you get with thick parts. You couldn't make a wind turbine blade from it. But for thin pieces, you can go really quick. So this is a quick look at the BMW. We'll quickly play this other video in a minute, which shows you inside the factory that makes you the BMW i3. The other main application of carbon fiber in the automotive world is in the 7 Series BMW. So here, the way they approached it changed. This was mainly RTM. Here, this is mainly compression molding of prepreg. RTM had more quality issues and higher reject rates and dry spots and lots of trim in the process. You'll see that here. The prepreg is more industrial. You take a roll, it's already sorted out, and you compress it and you trim it. So it's very robust. And also the volume went up from 100 cars per day to 300 with the 7 Series. 4,000 parts per day being made for the 7 Series. It's quite a lot of pieces, you know, from a thermoset process. And yeah, they changed their philosophy a bit. See if we can get the next one to work. Don't know why there's no sound. Fiber, strip fabric, many layers, kit. What the Germans have done is completely awesome. Picking up a layer of the long-term fabric. Very popular. It's this is a preforming tool, so this is got some powder binder in, and they're preforming the dry long fabric into a preform in a press. Now picking up the preform using vacuum suckers. Trim off the weight on the preform. Here is it is for 1,000 vehicles a year. It's from a lot of carbon fiber. So they're trimming off material they don't. They're taking that out, like seat pillar of a car, and here you see the first person kind of pushing that on. So that's now a dry preform ready for RTM. Picked up, it's placed in the Schuler press. So you can see it's slower than a thermoplastic, but very automated, very big press. And now the high pressure RTM process in general in around 40 bar, about 3-minute cycle time. We skip that video. Way there. That's now the side by 3 made in one piece. And they're now trimming this with a water jet cutter like you saw in the video. And actually go on to show you the whole of the production line. The video is quite long. In your own time, you can see everything is made, technical panels. Okay. So that was automotive, kind of state of the art. Last section will be around wind energy. So wind turbines, these are huge composite structures. And it's not until you see the scale of the people next to them that you really understand what's going on. So that's a 5 megawatt blade. This is a system being assembled. So they are really big composite structures. And we're going to see growth in these. My semester project actually in the 1990s, when I was doing my degree, was on wind turbine blades. Okay, I did some impact testing and some thermography and some fatigue testing after damage. And back then, it was really, it was an emerging way of making energy. That's only 2012. It's carried on growing. And it hasn't just grown in terms of capacity, they've also got bigger. So today we're at 125-meter diameter. Okay, so for those of you who climb, you know, that's 2 climbing ropes, 60-meter ropes, one this way and one that way. Okay, it's a big thing. And in the future, they're going to get still larger. What we see is the constituents of materials, and carbon fiber is here, as is glass fiber. Okay. And with all the needs to generate renewable energy, we're going to see a lot more wind turbine blades being used, and this is going to need composite engineers to improve how blades are made, etc. So again, just showing you what a blade looks like when it's being made. The main reason why composites are used in wind turbines is fatigue. And if you look at cycles in an aircraft and a helicopter, this is the number of cycles that we see in the application. A wind turbine blade's got a 30-year design life, which ends up being 10 to the 9. It's gigacycle fatigue. Okay, aluminium alloys don't have a defined fatigue limit. Okay, they just keep on reducing the ultimate stress with cycles. Steel runs out, but you reach a certain stress after which it continues to perform. And so do composites. So at a certain stress level, you can run basically indefinitely. So they're excellent in fatigue, and that's glass composites. And that's why you don't see aluminium wind turbine blades, because they are light, and you don't see steel because they'd be so heavy, be absolutely humongous. So glass has found a very natural niche, and there's some nice databases around high cycle fatigue of composites. These are the main elements of a wind turbine blade, and this is the last video in this lecture. It explains it much better than I can. We're just going to step into this video, and they show you how a wind turbine blade is made. Again, we're not going to watch it all. Just jump in. Basically made of 2 shells. Blade. You put your fiberglass mold. Okay. Mostly, otherwise you have 3 blades. They're different weights. They're going to wobble on. Then you assemble the shells together with the wedge in the middle. So that just shows you far better than I can explain how it's made. And We'll look in the third lecture again at recycling of wind turbine blades and what some of the trends are there and what can be done. Okay, we talked about the spar cap. If you just remember that, spar cap is this area here. People are starting to use carbon fiber in these for longer blades. And Zoltec, for example, is making a Pultruded spar cap, takes carbon fiber, 50K roving, and impregnates that with a resin, and it makes a UD strip that can then be built up to make the spar cap. So that's where carbon fiber is being used. And the other area of research that companies are looking at is changing the formulation of e-glass to a higher performance glass, where you get a 25% increase in strength just by changing the glass formulation. Okay, it's also higher stiffness, not very much, but the main change is in strength, strain energy, and an even bigger increase in fatigue resistance. So it's a big enough market for them to develop specific glass grades. Okay, so what we've seen are that composite materials are an established material class in aerospace, automotive. It's kind of early adoption, I would say, with significant use in wind. So that's really the first lecture, is just to set the scenery before we go into the next lecture, which will be around sustainability and the circular economy, leading into what about composites? How can we transition composites into a circular economy? So thank you for your attention. We'll take a quick 5–10 minute break.